Hello everyone, I'm Song Li from Xiamen University, China. It's my pleasure to introduce the cloudwork technology and the Xiamen University's joint effort for CHiME challenge. Here is the outline of the presentation. I will introduce from the 6 aspects. First, I will briefly introduce all systems, and then the details of all systems for track 1 and track 2 will be introduced. Next is the results of all experiments. Finally, make a summary of conclusions. For rank A of track 1, we consider the following 5 aspects: front-end speech enhancement, acoustic model, alignment and strict cleanup, chain model tree leaves and model fusion. For the rank B of track 1, we also tried language model, reciprocal, and entrance model. For track 2, we mainly explored acoustic features and the acoustic model, clustering algorithms, and variational Bayesian refinement. The overall framework of rank A of track 1 is shown in the figure, which is mainly divided into 4 parts: GMM, HMM training, front and speech enhancement, DNN HMM training, and decode. For speech enhancement part, we used narrow WP with the same configurations as the baseline system for derivations. Due to unmarked silence between words, the annotation provided from dataset are not perfect presets. Hence, we provided frame-level alignments for GSS from a well-trained SR model to get better separation. We also tried two beamforming methods, including beamforming and NN-based video beamforming. The one data is used as a target for NN-based video beamforming training. But we found that the performance of NN-based video beamforming is less than beamforming. So, we use beamforming in our experiments. Finally, we average the left and the right channels of one data to get better training data. For data augmentation, traditional speed and volume perturbation are applied in the training pipeline. Reverberate and noise argument are added to one data to simulate real microphone area audio. The IRR was generated according to training data flow plans configurations. In addition, 24 and 12 microphone GSS has been employed to augment training data. Finally, spec augments are also performed during training. In addition to the GMM-HMM standard training process, we have made 2 improvements. First, we train a GMM-HMM model with clean one data and decode with training data. We found that several alterations were not matched to the transcriptions, so we removed them, which had high WGR. Moreover, we added the removable that we designed according to the flow plans to the one data for the next stage of training. In terms of natural network acoustic model, we tried 4 different structures. The details are shown on the right figure. The first is ResNet CNN TDNF self-attention, including 6 layers convolution natural network with skip connections every 2 layers, 14 layers TDNF and a time-restricted self-attention block. The second is ResNet CNN FSMN, which includes 6 layers convolution natural networks with skip connections every 2 layers, and 14 layers FSMM blocks. The third is spec argument CNTDF, including spec argument are applied in the front of 6-layer CN blocks, followed by 14 layers TDNF. The fourth is multi-CN TDNF, which includes 3 6-layer CN blocks with different convolution kernel size, concat by 14 layers TDNF. Due to the complicated representation of audio data, CMM may be inaccurate for phonetic alignments. Thus, we trained a CHiME model without subsampling for alignment, which has shown improvement. In addition, various signal one as modeling, unit, or experiment, and we found that tree leaves are good to be set to 5,000, which is better than baseline. Finally, we tried two training objectives, LFMMI and LFBMMI, and tried to combine them. For decoder stage, we tried different speech enhancement algorithms for development and evaluation set. As shown in the red figure, the best result is GSS with alignment obtained from a well-trained ASR model. For the final result, minimization risk lattice combination is applied to all 4 models for the purpose of better performance. In rank B of track 1, we tried two rescore methods. First, the lattice generated from HCL GPRN FSD are rescored through a parent LSTM-based language model. In addition, we extracted best from the lattice and performed rescore. Frontier model. The intelligibility of the speech after front-end speech enhancement can actually present the accuracy of the speech recognized systems. In other words, the speech recognized system may have a center mismatch with the speech enhanced data. To solve this problem, we use a framework for joint training of speech enhancement and speech recognition, proposed by Shinjin Watanabe et al., named ME2E. ME2E consists of 3 components: a distribution subnetwork, a beamforming subnetwork, and an attention base (ASR). The left figures illustrate the architecture of ME2E. The training process is shown on the right figure. First, we use the one data to train attention-based model. Second, we use one data and arrow data to train the distribution subnetwork and the beamforming subnetwork based on MSE and SISNR objectives. One data is the level for training. Finally, we train the attention-based ASR model together with the 2 speech enhancement networks. In track 2, we mainly use 3 different configurations of acoustic features: 23-dimensional MFCC, 40-dimensional MFCC, and 40-dimensional F-bank. We have considered 2 different embedding extractors. The first embedding extractors we used is the official pre-trained direction model. X-vector DNN is trained with the VerseLive data, and the PLDA model is trained with the CHiME6 data. We used the same data to train our models, with a different architecture and features. In order to make speaker embedding have better distinction between classes, we choose the factorized time-delayed natural network (TDNF). It has excellent performance in speaker-recognized tasks. Besides an experiment, we choose to use 40-dimensional F-bank to train this model. The SAD model is same as the baseline. In addition to SC used by the official baseline, we also explored the spatial clustering, but the performance is not good than HC. After segment level clustering, because embedding segments are too quantized, we use variational Bayesian refine the mark binaries. The following two tables list our results. The results of hybrid system for track 1, rank A, are 21.65% and 40.24% WER and development and evaluation set. For rank B, 40.25% and 39.62% WER were achieved using hybrid systems, along with 56.9% and 50.6% WER for all end-to-end systems. The results of track 2 category A are 47.72% DER, 61.85% JER, and 77.5% WER for development set, and 65.36% DER, 67.32% JER, 72.52% WER for evaluation sets. Finally, I will make a summary of conclusion for our effort. First, using the frame level alignment provided by ASR as the labels of GSS can improve the performance of GSS. The CHiME model without sampling provide better alignments. Removal of high WGR speech during training can improve model performance. Different decision tree leaves can bring different performance to the model. Spec argument is a kind of effective data argument method. Model fusion can improve recognized performance. Language model rescore is an effective post-processing method. Finally, end-to-end SR in more difficult settings like reverberate, noise, and far-field calculations still lag behind. Thank you for your watching. Any questions?